The $2 hydrogen dream is more than just a cost target. It's the finish line for the clean energy race. Every major hydrogen developer, investor, and policymaker around the world is chasing it. But what if the breakthrough that finally gets us there doesn't come from new electrolyzer chemistry or another government subsidy, but from something entirely different? 3D printing? Yes, the same technology used to build aerospace parts, medical implants, and rocket engines is now being pointed squarely at one of the biggest bottlenecks in green hydrogen: electrolyzer manufacturing. In today's episode, we're diving deep into how 3D printing, also known as additive manufacturing, could make $2 hydrogen a reality sooner than anyone expected. To understand why this is such a big deal, we first have to understand what's slowing hydrogen down. Green hydrogen is made by splitting water into hydrogen and oxygen using electricity from renewable energy. It's elegant in principle but messy in practice. The electrolyzer, the machine that does this, is incredibly expensive to build. Why? Because the core of the system, known as the stack, contains hundreds or even thousands of delicate precision machined parts. Bipolar plates, flow channels, membranes, seals, and manifolds. Each of these components must be manufactured to microscopic tolerances, assembled in clean environments, and tested for leaks and electrical losses. The materials are exotic and pricey: titanium, iridium, and specialized polymers. And the supply chain that produces them is slow, centralized, and fragile. That's why today's electrolyzers can cost anywhere between $800 to $400 per kilowatt. For hydrogen to hit $2 per kilogram, that number has to come down a lot. And that's where 3D printing steps in. In 2014, researchers at the University of Glasgow quietly demonstrated something remarkable. Led by Professor Leroy Cronin, the team used a simple desktop 3D printer to fabricate the flow plates inside a small electrolyzer. Not from titanium, but from polypropylene plastic coated with silver. The result? A working electrolyzer cell that weighed 4 times less than its metal counterpart and cost a fraction to produce. One of their 3D printed flow plates cost just 17 cents in materials compared to 80 cents for titanium, while offering similar performance for early-stage lab testing. It was a proof of concept, an elegant message that said, what if the components of an electrolyzer could be printed instead of machined? Fast forward to 2025, and that question is no longer hypothetical. Researchers around the world are taking it seriously, and companies are starting to act on it. Additive manufacturing allows engineers to build highly complex, lightweight, and customized geometries that can't be made through traditional machining. For electrolyzers, this means printing flow plates with optimized gas channels, integrated cooling systems, and internal manifolds in a single print job, eliminating multiple assembly steps. It also means experimenting with new materials, conductive polymers, composite coatings, and even metal powders fused with lasers to create corrosion-resistant plates. Every gram of weight saved and every minute of manufacturing time reduced pushes hydrogen closer to commercial viability. But let's zoom out for a second. The real magic of 3D printing isn't just its precision, it's its flexibility. Imagine being able to print electrolyzer components locally, right next to a wind or solar project, instead of waiting months for machined plates to ship from across the world. Imagine being able to tweak a design overnight to suit local pressure, water purity, or cooling conditions, and then print it immediately. That's what distributed manufacturing makes possible. It decentralizes production, shortens lead times, and reduces the risk of supply chain bottlenecks. One of the biggest hidden costs in the hydrogen industry. Take the German company Exentis Group. They've been making headlines for applying additive screen printing to produce micro-precision metal plates for hydrogen systems. Their 3D printed stainless steel components can include channels as fine as 125 microns, thinner than a human hair. And they can produce over 1,000 plates per day on a single system. That's industrial scale, not lab scale. By proving that high-throughput additive manufacturing is possible for hydrogen hardware, Exentis is showing how the industry might escape the prototype trap and move into true gigawatt-scale production. It's no longer just about fancy geometry, It's about mass manufacturing at the speed of demand. At the same time, academic research continues to push performance limits. A 2025 review by Kahn and colleagues analyzed over 100 studies on 3D printing and hydrogen electrolysis. They found that 3D printed electrodes improved the hydrogen evolution reaction by 27%, while 3D printed flow plates boosted power output by 57%. In practical terms, that means better efficiency, lower power consumption, and smaller stacks for the same hydrogen output. Exactly the kind of engineering edge needed to make $2 hydrogen achievable. Another group at Stanford University took a different approach. Instead of printing polymers and coating them, they combined stereolithography with electroless plating, essentially printing plastic parts and then chemically depositing a metal layer on top. The result was a lab-scale electrolyzer that performed just as well as a traditional machined titanium version, but at a fraction of the cost and build time. Their goal wasn't to commercialize the unit, but to prove that design iteration in electrochemistry can move at the same speed as software. In other words, print, test, redesign, print again, all in days instead of months. That kind of agility is how hydrogen technology will accelerate from prototype to product. Now let's talk economics, the part investors care about most. When people hear 3D printing, they often think of expensive one-off parts. But in the case of electrolyzers, the economics are surprisingly compelling. Flow plates and bipolar plates represent a large share of stack cost, sometimes up to 30%. If additive manufacturing can reduce those costs by even 20%, it could shave a few cents off every kilogram of hydrogen produced. That may not sound like much, but in a market chasing $2 per kilogram, a 10-cent reduction is a huge competitive advantage. And when you combine that with lighter stacks, shorter logistics chains, and less scrap waste, the total system-level impact compounds. There's also the sustainability advantage. Traditional machining wastes a significant amount of raw material. You start with a solid block of metal, cut away most of it, and discard the leftovers. Additive manufacturing builds from the ground up, using only what's needed. Less waste means less energy, fewer emissions, and a lower carbon footprint, aligning perfectly with the ethos of green hydrogen. And when 3D printing uses recycled powders or biopolymers, the environmental story gets even stronger. So who's leading this movement? Beyond Exentis and the universities, several companies and startups are eyeing this frontier. Traditional flow plate manufacturers like Switzer Manufacturing in the US and Eisenhuth in Germany are already making advanced metallic plates for hydrogen generation and purification. While not yet fully 3D printed, their adoption of digital design and precision fabrication makes them prime candidates for additive transition. Large stack makers like Siemens Energy and Electric Hydrogen haven't formally announced 3D printing in their stack production. But as they build gigafactories capable of churning out megawatts of electrolyzers every month, it's only a matter of time before additive manufacturing becomes a cost-saving step in the process. The trend is inevitable. As demand for hydrogen stacks scales into the millions, manufacturing innovation becomes the make-or-break factor. But let's look ahead. What happens when 3D printed electrolyzers move from lab curiosity to industrial standard? One possibility is local production. Regions with abundant renewable energy but limited heavy industry, think Africa, Southeast Asia, Latin America, could print electrolyzer components domestically instead of importing them. This decentralization could make green hydrogen a truly global industry, not just one dominated by a handful of manufacturing hubs. Another possibility is design democratization. Imagine open-source libraries of electrolyzer component models, flow plates, manifolds, seals, that can be downloaded, printed, and customized anywhere. That could ignite a wave of small-scale innovation, similar to what we saw in solar and electronics. Suddenly, the barriers to entry drop, and hydrogen becomes as accessible to small developers as solar was 2 decades ago. The implications go even further. 3D printing could make electrolyzers lighter and more compact, enabling new use cases like portable hydrogen generators, modular off-grid systems, or even hydrogen drones. Combine that with AI-assisted design where machine learning optimizes flow channels for minimum pressure drop and maximum gas separation, and you have a new era of intelligent manufacturing. The electrolyzer of the future might not just be printed, it might be algorithmically designed, printed locally, and assembled on demand. That's a manufacturing ecosystem fit for the 21st century energy transition. Of course, every innovation comes with its challenges. 3D printed parts must still meet strict standards for conductivity, corrosion resistance, mechanical strength, and long-term durability. Silver coatings can oxidize, polymers can degrade, and metal powders can be expensive. Scaling from lab to industry also requires robust quality control. You can't have variability in plates when you're stacking hundreds together under pressure. But these are engineering challenges, not deal breakers. Every technology, from solar PV to lithium batteries, faced similar hurdles before achieving cost parity. The same playbook will work here. Iterate, scale, standardize, automate. The timing couldn't be better. The global electrolyzer manufacturing pipeline is growing at an unprecedented rate. More than 200 gigawatts of projects are now in development worldwide, with demand far outpacing supply. Gigafactories in Europe, the US, China, and the Middle East are racing to fill the gap. Yet even with massive investment, bottlenecks remain, especially in machining flow plates and sourcing raw materials. That's why additive manufacturing is not just a nice-to-have, it's a necessity. Without faster, cheaper, and more localized manufacturing methods, hydrogen's cost trajectory will stall. 3D printing is the shortcut that could keep the industry on track toward the $2 target. Let's imagine how this plays out on the ground. A developer in Morocco partners with a local additive manufacturing firm to print customized flow plates for a desert solar hydrogen plant. In Australia, a mining company prints replacement electrolyzer components on site, avoiding months of shipping delay. In the United States, a startup integrates 3D printed electrode structures into a $10 million PEM system, cutting stack mass by 30%. Each of these stories contributes to a larger narrative, the convergence of clean energy and digital manufacturing. And that's the future we're heading toward, one where energy infrastructure isn't just built, it's printed. For developers and investors, the key takeaway is simple. Manufacturing innovation is now a critical part of hydrogen economics. The cost of renewable electricity has already dropped dramatically. The next big lever is hardware. How we build, source, and scale electrolyzers. Whether it's printed flow plates, laser-sintered manifolds, or additive fabricated electrodes, every layer of cost reduction matters. Those who adopt these technologies early will have a competitive edge. They'll build cheaper plants, deploy faster, and reach profitability sooner. The companies that cling to legacy manufacturing methods risk being left behind. So, how soon can 3D printing actually make $2 hydrogen possible? If current research continues at its pace and manufacturers like Exentis, Siemens, and Electric Hydrogen begin integrating additive processes by the late 2020s, we could see stack cost reductions of 15 to 25%. Combined with renewable energy prices dropping and improved efficiency, that's enough to push levelized hydrogen costs below $2 in many regions before 2030. In other words, this isn't science fiction. It's a manufacturing revolution already in motion. To close, let's go back to the vision. The hydrogen economy isn't just about molecules, it's about machines. The machines that make those molecules. 3D printing represents a paradigm shift in how we design and build those machines. It promises faster innovation, local production, and massive cost compression. The exact combination needed to scale green hydrogen globally. In a world that desperately needs clean energy at scale, additive manufacturing might just be the bridge that gets us there. If you're a hydrogen developer, investor, or engineer, it's time to start paying attention to where your electrolyzer components come from and how they're made. Visit https://h2hub.reneenergy.com to explore how tools, templates, and feasibility kits can help you model your next hydrogen project, and join the conversation about the manufacturing revolution, reshaping clean energy. Because the future of hydrogen won't be built in factories alone, but it will be printed, optimized, and deployed at the speed of innovation.